I've given this talk before at Hacktivity in Budapest. So this is basically just a webinar form for that. And we're going to talk about Windows kernel exploitation. So before we jump into the topic, just a bit about me. And Robin mentioned that already. I'm part of Enviso's red team, the adversarial risk emulation and simulation team, short ARIS. That means that we do Tiber engagements, we do classical red teaming, both stealthy and non-stealthy. We do purple teaming, and I also do a lot of R&D to improve our internal tooling and help us with these red teams. Next to my job with Enviso, I'm also a SUNS instructor for the SUNS Sec 670, which is red team tool development, so building C2 tooling in C++ and so on and so forth. So a bit about this talk. So first, a word of or a bit of expectation management. So there will be nothing new. There won't be any 0 days in this talk. This talk is more a bit of a foundational talk so that a red teamer or also the blue team side can understand why we even need kernel exploitation in a red team scenario. So doesn't that sound a bit overkill? But then we'll also talk about how a driver can be exploited, how we can interact with the driver, how we can send data to a driver, and how we can use that to exploit a vulnerability. But we'll also talk a bit about what we can target as part of the exploitation process. So what kind of data or what kind of exploit primitives can we use to actually gain an advantage during a red team scenario? So there will be some theory, and I'm already sorry about that, but it is just required to understand a bit about what's going on once we look a bit deeper into the driver exploitation side. So why should we even bother with the kernel? Simple answer is because the defensive tools that we as a red team are up against, they do too. So especially with Microsoft Defender for Endpoint being easily available to a lot of organizations, especially in the red teams that we do, we rarely encounter any company not running at least one, sometimes even two different EDRs in their environment. And most of these EDRs have a kernel mode component. So now why is that interesting? Because if you go on LinkedIn, you'll often see people boasting about EDR bypasses and fully undetectable tooling. And when we think about how an EDR works, we can easily determine that most of these are not real bypasses and are not undetectable. They may be undetected at the time, but the EDR has a kernel mode component, and if your bypass is fully in user mode, that means that most EDRs will still be able to gather telemetry, and then later on that telemetry can be analyzed and your payload can be detected, especially in a mature environment. When you have a threat hunting team, they will be able to determine your presence based on telemetry that you think was not there, but because it's in the kernel and you're still operating in user mode, it was never fully bypassed. So that means that if the EDR is in the kernel, we should be too, and we should be able to neuter these telemetry services. For example, callbacks in the kernel that we will be looking at later when we talk about the targets, but also things like ETWTI, so event tracing for Windows threat intelligence, which is a kernel mode interface for advanced telemetry for a certain set of system calls. So what can we do with kernel mode access if we choose to, for example, deploy a kernel mode exploit during a red team? So what we can do is we can disable signature requirements. So Windows requires drivers to be signed. So that means that if we write a rootkit, if we would want to deploy it on a system and we don't have this exploit, we would have to send our driver to Microsoft to get it signed. And I mean, it happened before that APTs did that, but in general, we do not want to have Microsoft have access to our code and our driver before we want to deploy it. So by exploiting a driver, you are able to disable these signature requirements, and you can load your rootkit even if it's not signed. There should be a small asterisk to that if you have virtualization-based security, there are a lot more limitations Also when it comes to signature requirements and so on, and especially tampering with those. But that is a bit beyond the scope of this talk, so we're not going to talk about that in this talk. And of course, you can do the, let's say, classic kernel exploitation, which would be privilege escalation. So if you would see a driver like this running on a system and you know it's vulnerable, you could access the driver and exploit it to gain privilege or to gain higher privileges on the system. And that's what we're going to, as one of the use cases that we'll look into a bit later. The second use case that we look into is disable and or tampering with callback routines and the tracing providers that I mentioned. And those are basically functions that you can create in a driver and then register with the system so that every time, for example, a process is created, a thread is created, your driver is notified about that creation, and you can look into for example, the process creation and what parameters were passed into that, so you can make a decision if that was a malicious process or a benign process. And then last but not least, you can use a kernel exploit to disable process mitigations. For example, protected process, if you think about things like else's. One word of warning, though, especially if you hear about things like tampering and disabling and changing things. In the kernel, if you make a mistake, it will take down the system. So if you do user mode exploitation, you might crash a service that's then restarted. But if you make a mistake in the kernel, you have your wrong offsets or something like that, it will crash the whole system. And that's not only bad for stability in general, but it might also alert someone that something is going on in the network, especially if you crash multiple systems at once. And I'm definitely not going to make a CrowdStrike joke at this point. But yeah, that's one of the best cases where it shows how dangerous it can be to mess with things in the kernel. So before we look into exploitation itself, we need to go over a few internals. I'm trying to keep those as short as possible, but it's just a few things that we have to do or that we have to talk about to understand what's happening. So if you've ever done anything with the kernel or system internals on Windows in general, you're probably familiar with this diagram taken from the Windows internals book. And there are a few important things in the Windows kernel, and that's the kernel itself. So the kernel exposes a few internal mechanisms that are important for the operating system. That includes things like thread scheduling. Then we have the executive that in turn provides a lot of the core functionality of the operating system. And then below that, we have the hardware abstraction layer. And that is often important so that basically that the same operating system can run on different sets of hardware without the operating system having to be adjusted for different sets of hardware. So that's a very high level overview. So three important components. We have the kernel, the executive, and the hardware abstraction layer. When looking into the Windows kernel, there's a concept called rings. And rings is what separates user mode and kernel mode. So in theory, there are a lot more rings than what's used in Windows. Ring 2 and ring 1 is not really used with Windows, but instead we have ring 3. That is our user mode. So this is where all our applications are, like Word or Excel. On the other hand, we have kernel mode. And kernel mode is where the kernel itself lives. That's where the kernel memory lives. And there are a few differences between those two. For example, in user mode, if you have an application, the application has a set of shared memory, virtual memory space, where it has basically like its own set of memory. And the difference is that in kernel mode, virtual memory is shared, or is just one big blob of memory, so that if you are in the kernel, you can access everything else in the kernel. And that is quite critical, because if we look at virtual memory, that means that there's no separation between things. So that means that if you are a driver, you can read and write from kernel memory as much as you want. And that is also what comes with a bit of risk, because you have access to critical kernel mode structures and information that if you write to those kernel mode information and structures, what might happen is that it causes the system instability that I mentioned before. And so the risk with kernel mode, that's both the advantage and the risk of kernel mode exploitation, is that you can corrupt these critical structures in the Windows kernel, but you also need to be very careful and very cautious about what you do in the kernel, because there are no safety mechanisms, there's no hand-holding anymore in the kernel. So if you write to the wrong location, it will take down the whole system. Okay, so with a bit of the basics for the individual components out of the way, the next thing that we need to talk about is how do you interact with drivers and what are drivers actually? So you can imagine a driver as a more or less like it's a portable executable. So it's like an executable or a DLL in user mode. It's just the difference is that it's destined for kernel mode. So those drivers are loadable kernel modules. They are, of course, executed in the context of the kernel. And in general, there are different forms of drivers. So, for example, hardware drivers that are used for interactions with monitors, graphics cards, peripherals. But what we are looking into are software drivers. So these don't have to be tied to anything hardware, but they are basically just like modules in the kernel that can be used to extend the functionality of the kernel or access functions that are not available to user mode. There are a few different models that, depending on what driver you're writing, you have to choose the right model. But for this talk, we are focusing on the legacy NT model, because most of the drivers that are exploited in a bring your own vulnerable driver capacity, like we're looking into today, are of the legacy NT model. And what's characteristic for this model is that every driver has a driver entry function. So that is defined, and you can imagine that like the main function in an executable or the DLL main function in a DLL. So that's what the loader uses to actually initialize the driver and call in the driver, and how the driver itself is initialized. The second concept that we need to understand are I/O request packets. So the Windows I/O manager, that's a component of the kernel that's responsible for making sure that our information goes from user mode to the kernel mode drivers. And so every time we talk to a driver, those information that we want to send into the driver, very like simplified, are packaged up into a so-called I/O request package, or ERP for short. And that is a structure, an internally defined structure that basically contains all the information that the driver will need to fulfill its functionality. So if the driver, for example, offers a function that will send something, for example, to a peripheral, then the ERP would contain anything that the driver needs to send that message onward. And through these ERPs, the good thing is that we have a consistent way of talking to drivers. And why that's important, that especially if we are looking for vulnerabilities, we know exactly what we are looking for and how we can identify certain pieces of code, for example, where we know that, okay, this piece of code takes requests from user mode, and this piece of code processes data that come from user mode. And because we have this consistent way of talking to drivers, that makes this process a bit easier for us. Then to actually talk to the driver, what we need are so-called I/O control codes. So again, a bit simplified, but most drivers work in a way that we have more or less a switch case. Like you can imagine it like a large switch case statement in code, or a dispatch table, where we send a certain code, a certain opcode, or in this case, the I/O control code, to the driver, and depending on the I/O control code that we send to the driver, a specified function will be executed that's defined in the initialization routine of the driver. And this is important to understand because it helps us to dive into drivers and reverse engineering and looking for vulnerabilities in drivers, because it has so many similarities that once you understand these I/O control codes and the control flow in general of how these are processed, it's often easy to identify where things are processed in the driver, and then from there you can start analyzing the individual functions. So what we need to interact with the driver is an open handle to the driver. And the good thing is that we can just use create file, because when a driver is created, it is basically, it creates a device, and we can use create file with that device to get a handle to the driver, which you can then use in here with the device I/O control function, and that is the actual function that will cause our packet, our data, get sent to the driver. So what's passed to the driver is basically just memory. So we can see that we have here the LP void LP in buffer. So this is just our pointer to a buffer that gets sent into the driver with a size attached to it, and then what the driver most often does is it will cast it into a structure or use data at certain offsets. And that's one thing that during reverse engineering that we need to figure out is how does the structure that the driver expects look like, so that we can send the correct data to the driver and it will not crash because it tries to access memory that we haven't initialized yet. So this is one of the critical pieces of exploiting drivers, is understanding what kind of data types the driver expects, so we can fulfill those requirements, and we can go down to the vulnerable path. So that's what I mentioned before. IOCTLs are often passed in switch case statements. So on the right here, you see a part of the disassembled and decompiled code. And as you can see, it is actually decompiled down to a switch case statement, where then each of the case statements are the I/O control codes that are expected by the driver. So talking about kernel mode vulnerabilities. In a lot of blogs, you'll see that, and especially those talks or those blogs that look at the beginner level and foundational level, you'll often see stack buffer overflows. So it's very similar to what you see in user mode exploitation, where you start with Windows 7, 32-bit, stack buffer overflow to understand the concepts. And it's good for introduction, but I think in most cases stack buffer overflows are not, at least from what I've seen, not that exploited and exploitable anymore. But instead there are other vulnerabilities, and that's what we're going to look at today. There are, of course, because as with user mode, you have a heap in the kernel. So you can have, and the heap in the kernel is often referred to as pool. So you can have pool overflows or heap overflows. You can have classical use after free vulnerabilities where data is first freed and then referenced again, leading to all sorts of problems. Then, of course, race conditions and logic bugs. There's a great free training on kernel mode exploitation that has both the use after free vulnerability and the race condition exploited in tandem. And if you want to get started with kernel mode exploitation, I really recommend looking into that. It's by Open Security Training, so definitely recommend that one. But for this case, we're looking at a write what where vulnerability. most of all because that is very trivial to exploit, but it also bypasses a lot of mitigations that are in place because you can perform what's called a data-only attack that we'll look into in a bit. So before we can get into actually running an exploit, one thing that we do need is a kernel memory leak. Now, for the simplicity of this workshop or this talk, I'm focusing a bit more on the built-in kernel memory leaks of the Windows operating system, with the small limitation that as of the latest version of Microsoft Windows, so Windows 11 24H2, a lot of these do not work anymore because Microsoft actively mitigated those. But in general, when we work with the kernel, we have the issue that a lot of things are based on offsets. And that means that, first of all, these offsets are specific to a certain version of Windows, but we also need the base of the Windows kernel to use these offsets and to basically access data at a certain offset. Now, like the drivers, the kernel itself is basically a portable executable that's running on the system. And like a executable or a DLL, the kernel itself has an image base address where the executable module is loaded. Now, the Windows operating system offers a few different APIs like enum driver or entry query system information with the module information class that will actually give you a list of all drivers on the system, and then you can use that list of drivers on the system to compare it against NTO's kernel, and then you can use that to retrieve the base address of the actual Windows kernel. These work from medium integrity level. So for example, if you want to exploit a driver from the browser and you are in low IL, so low integrity level or sandboxed, these functions luckily do not work. But if you're just executing it as a normal interactively logon user, then you can use those APIs to actually get the base address of the kernel and combine that with the offsets that you have determined before to access data in the kernel. Now, if you look into driver exploitation a while back, you'll probably see that Microsoft in the meantime has done a lot of things. So a lot of the attacks that you see in blog posts that are from 5 or more years ago, they might not work. Best example is it used to be possible that if you have a null pointer dereference, you could just map the null page. So you could just map a page of memory at address 0, and then when you had a null pointer dereference, because you put data at address 0, the null pointer dereference would not lead to a crash, but it would dereference the data at the null page. So what Microsoft did is they just mapped the page and make it not accessible to be mapped. So this is basically fully mitigated, and exploiting null pointer dereference in a modern Windows operating system is, I would never say impossible, but it's very difficult to find an exploitable condition. And like in user mode, we have data execution prevention in kernel mode. The same goes for ASLR. So a lot of things are randomized in the kernel, so it's not that easy to predetermine certain memory locations. That's why we need to work with the image base and offsets, because that's how we can defeat kernel mode ASLR. And then one important mitigation is also supervisor mode execution prevention. And that is a very, I wouldn't say simple, but it's kind of simple, but equally effective mitigation, where basically the kernel determines that if a user mode process wants to execute memory in a kernel mode process or a kernel mode, if you're in kernel mode and you want to execute memory in user mode, the kernel will prevent that. So if you look at older blog posts, you'll see that they just map shellcode in user mode and then execute that shellcode in user mode from kernel mode. And that's exactly what supervisor mode execution prevention tries to block. So there are also bypasses around that, but that's what we're going to focus on. The good thing is with the write what where exploit that we have and the data only attack, supervisor mode execution prevention is not relevant to us because we won't be executing anything in user mode, but instead we are using the kernel mode write to manipulate data directly. And then of course, virtualization-based security and hypervisor-based code integrity are like the new kids on the block that introduce a lot of complexity because basically the operating system is now suddenly virtualized, and we cannot access certain kernel mode memory even if we do have full access. So as I said, data only primitives and direct kernel object modification, short for DCOM. So not DCOM with a C, but with a K, that can be exploited through write what where vulnerabilities are a very powerful exploit primitive because we don't have to execute any code. But the theory behind that is we use a vulnerability where we have the ability to read and write data from the kernel to modify the data in the kernel without shellcode, but by doing it directly through the vulnerability. So I tried to go over this really quickly, and it's by far not as in-depth as I would want this to be. But for time permits, it's basically the basics, the foundations of the different components and functionalities that you need to start looking into kernel mode exploitation. So now let's take a look into a practical example. And the example that I've chosen is actually a anti-cheat tool. If you've ever looked into kernel exploitation, you probably know that there are a lot of kernel mode anti-cheats that are just completely badly written and can be exploited quite easily. And the reason why I chose this tool, this echo anti-cheat, is because the vulnerability itself is so trivial that I really like it for showing the idea or for showing how these vulnerabilities can be exploited, because it is very actually easy to exploit in comparison to a lot of other vulnerabilities where you have to take a lot of steps to be able to get into exploitable condition or where the write is limited. But in the case, and of course, this is nothing that I have found. This is based on a public blog post for CVE 2023-38817. So not my vulnerability, but I really like that vulnerability because it's really good for teaching how this kind of stuff actually works. Now, the cool thing about this vulnerability is that we basically have an IOCTL, so an IO control code, that will allow us to do an arbitrary memcopy in the kernel. That sounds very dangerous because it is. It means that by passing this ioctl to the kernel, we can tell this driver to write an arbitrary amount of data to an arbitrary address in the kernel. We can also say we want to have an arbitrary amount of data memcopied, so copied from an address in the kernel to an address in user mode, to a user mode buffer. In the mitigations, I had supervisor mode execution prevention. We're not executing code, we're just accessing code. In theory, there is a mitigation called SMAP, so supervisor mode access prevention, that would actually prevent this sort of vulnerability, but that's not fully enabled on Windows yet. And I believe due to reasons of compatibility, as always, Microsoft is not able yet to fully activate this feature. But I believe they are currently trying to get everything rewritten in a way that they actually are able to activate this. So that might be also one of the primitives that might be killed in the future. But for now, we do have an arbitrary read by taking memory from the kernel into a user mode buffer and an arbitrary write by passing kernel mode memory, user mode memory to kernel mode using this memcopy. Now, I said it's easy to exploit. Unfortunately, you cannot just send the buffer and send the ioctl and it will just work. There is some setup code that that needs to be done. Let me just quickly restart that VM. So if we go back, if you go to, and this is Binary Ninja, and just look a bit at the code, one function that I renamed and that we have here is, and I fortunately cannot increase the screen size, so I hope it's fine that everybody can read it. But the dispatch IO control, this is the function that will be called once a ioctl is received by the kernel driver. And there needs to be a bit of setup in the driver before we are actually able to call the IO control code that we want to exploit that vulnerability. And the first one we see is that if if we enter this if-else condition, the first thing that is checked if the IO control code is not this one, ending in 9.4, then a global init var that I've renamed, so it's not normally called global init var, is checked. If that one is 0, basically a error will be returned and the driver will not process our IO control code. So that means that before we are able to go to the actual IO control code that we want to exploit, which is down here, ending in 2.4, we need to somehow set this global variable. And the fact that if it's not, that it compares if it's not this IOCTL gives us already an indicator. But if we go to the references, we can see that indeed here we have a function that I renamed to initialize global variable that basically does a bit of arbitrary cryptography. So uses bcrypt to generate some data. I didn't even bother with reverse engineering this more, and you'll see in the blog post that they didn't either. Because the only thing that it does is it initializes the global variable to the process ID of our current process. So what that means is that we have a IO control code down here, and basically this is the else condition to our check if it's not that IO control code that we need to call first. This will initialize the global variable, and now every subsequent call to other IOCTLs will go to these because our global variable has been correctly initialized. Go back to the slides. Okay, so that means that we do have the setup, and the good thing is, and that's why I still think it's not too bad in a sense of complexity, that this setup code is more or less the only thing that you need to take care of. There's a bit of access control by basically checking in the kernel every time a call is made if we do have access to the process that we're trying to copy memory to or memory from, but that can also be easily bypassed. So what do we need to do? First, to initialize or to pass the initialization code, we need to go through, oh, and I'm severely running over time. So yeah, I'm going to cut this short. So we basically set up the driver by passing a empty buffer. Then we have this bit of access control where we need to pass the current process ID with an access code. And if we do have access, which we'll probably do, then that means that the driver is good to go. And from there, we can just call our vulnerable function. And what I did in my code is I built a few primitives that basically says, for example, kernel read or kernel write, and then the size I want to read or write. In this case, in 64, so I can use that to write 64-bit 8-byte of data into the kernel. And with the read, I can read from the kernel, and then that's the same for the write. Okay, so privilege escalation. Really quickly. A process on the system is basically represented by a eProcess object. So every process running on the system has a kernel mode object associated to it. This kernel mode object tracks the privileges of that process through basically tokens that are used to control access to what Windows calls secureable objects. So traditionally, what you would do in a privilege escalation scenario, or what most of the blog posts do in privilege escalation scenarios, is they would go and take the token of a different process, for example, a system process, and copy it to the current process. So by copying a token from a high integrity process or system level process to our own process would assume these privileges. So the general procedure behind that would be to iterate over all processes on the system to find the system token, the system process, and our own process, and then copy using the write what where. We could then copy by reading and then writing from one process token to another. Now, what I like a bit more and what I find a bit more difficult to, also a bit more difficult to detect because it's not done so often, is that this token not only has information about who the owner of this token or who this token is basically belonging to, it also has information about which privileges, so which Windows privilege, like for example, SE debug privilege, are present in the token and are enabled. So because we have this data, what we can do is we can override the privileges that are held by the token using our write what where primitive. So these privileges are basically a bit mask that we can just overwrite to enable all our privileges. So to show how this works, let's do a quick demo. So we have our target system here. The echo driver is running on that system, and we have a command prompt here that is currently, if we do who am I, we can see user is Kevin. If we do who am I /priv to show the privileges, who am I, we can see that we have the default privileges enabled. Now, if we exploit the vulnerability to override the set and enable privileges, we need the PID of the process for 4936. So we can see that what this tool does, it gets us the kernel base. As I said, we need to leak the kernel base. Then we'll find the initial system process. We also retrieve the eProcess of our process that we currently have, so with PID 4936, which is our CMD. And then we look at the current privileges present. So these are all the privileges that are on this token. And then we can also see that the privileges enabled, that's only this one, and this would correspond to the SE change notify privilege. Now, what the program does in the background is it overrides the bit mask with a new bit mask that will basically set and enable all privileges. So if we do who am I again, I'm still the user Kevin, but if I do who am I, wrong one, if I do who am I /priv, we can see that now basically all privileges in my process are enabled and set here. It also means that while I'm still my own user, I can do things like delete Windows system 32 calc.exe. And if I now check it, we can see that calc has been deleted, even though I'm still in my own user's context. I can now delete or modify system files because I have the appropriate privileges, like, for example, the backup operator privilege. Okay. So technically, there's still a bit about kernel callbacks, but it's 11:45, so I'm slightly running over time. But to cut the privilege, to cut the topics about callbacks a bit short, the principle behind this is that you can register a callback, and internally, Windows tracks all registered callbacks by putting them in an array. The good thing is that what we can do is actually access this array because we have a vulnerability to write in the kernel. So in this case, this is what the array looks like. And it's basically just the pointers to the notify routines that are registered for, in this case, create process call. So every time a process is created, all these pointers here get called and the drivers get notified. And if we resolve that pointer, we can see that this one, especially, and that's no coincidence, points to WD filter, which is the driver of Microsoft Defender. So every time a process is created, Defender gets notified. So what we can do is to list callbacks, we just go over this array and then basically retrieve the pointer for each entry in the array and then do a lookup what module it belongs to. So, and this is again where we can then just exploit our read and write vulnerability to read from that array in the kernel, which we normally from user mode would not have access to, and then print the callback routine. Overriding a callback is basically just the same, where we use our write primitive to override a pointer at a certain location. So we calculate the offset into the array. Because we know that every entry in the array is 8 bytes, we just take the size of a dword, 64, so 8 bytes in general, and multiply it with our index into the array where we want to access the data. And by this, we can override the callbacks. So quick demo for this as well. So if we have our driver here again, so if we use the list callbacks function, we can see that it grabs the address of PS set create notify routine and then uses that to do some memory scanning and basically grab the address of the actual array from the body of that function so that we can then read and write that array. And we can see here that we do have the WD filter, so Microsoft Defender is active. Now, if we want to kill that callback, we can do delete callback, give it the index that we have right here. Then hopefully nothing crashes. Okay, see that it again grabs the handle to the driver, resolves our address, and then we override the callback ending in at this address. Now, if we list our callbacks again, we can see that compared to before, here we do have W filter, and in this case, W filter is gone. So by using this technique, we could then implement all the other callbacks there are, for example, object creation callbacks and thread creation callbacks, and then delete arbitrary callbacks from that array so that even an EDR with a kernel mode component would not be notified anymore. And this way we could actually bypass kernel mode telemetry and not just basically operating user mode. Okay. So quick demo. Luckily, everything went all right. So, yep. Wrapping up. As you see, I mean, this was like 50 minutes, so I'm trying to wrap up really quick. Kernel exploitation is rather complex, and it comes with a very steep learning curve because there are so many concepts that you need to dive into. But once you have these concepts down, once let's say the foundations are a bit clear, it becomes really rewarding really quick because you now have the capability to get around kernel mode telemetry that you normally wouldn't be able to get around if you would operate solely in user mode. So that means for us as red teamers, and I hope that there are some red teamers here that think, oh, maybe this is something that I should look into. This will give you like a first glimpse of what kernel mode exploitation will look like and the different concepts that are involved. Unfortunately, the timing is a bit bad to get into kernel mode exploitation because Microsoft does a lot of things currently to make this even harder. And with the current operating system released, 24H2, it's already quite hard. And I forget his name, Dave from Microsoft, he goes around different conferences and gives talks about different mitigations or other mitigations that they will be introducing. So it will basically become harder with every Windows release because they now focus a lot more on security. But in my opinion, it's still fun. I still quite much enjoy it. And I hope I could give you, or I was able to give you a nice little introduction into kernel mode exploitation, and some of you will pick that up as well. So now we have time for your questions.
All right. I want to thank you so much, Kevin, for this presentation and everybody for joining. Before we get into the questions, I just shared the link to a feedback form in the chat. It only takes a few minutes. It's a fairly short form. So please fill it out. It really helps us. I would say do it now while we're diving into the questions. Also, feel free to keep posting questions in the chat. I'll take over the screen sharing for a second. We had a first question, which was, do you have some more resources, some references about that anti-cheat exploit that you were using here? Is there any more material?
Let me check. So I converted the initial slides that I had into our own template, and I think I put the sources on everything. It might be that I missed one or two. Let me check really quick. Okay, it's not in there. I'll add the reference to the blog post to the slides before they get uploaded.
All right. Next question.
Wait, I'm not sharing
next to open security training, which training courses do you recommend to get into kernel driver vulnerability research and exploitation?
So I know that there's at least one very good training, and that training is by Hexis. So they do it, I think, at BrewCon, and I think that's a very great training to get into kernel exploitation. They also take you from the start all the way to modern Windows 11 operating systems for the different exploits, and they target or they talk about the write-what-where, what I just showed. They also talk about heap exploitation, stack exploitation, so it's pretty comprehensive, I would say. And then, of course, but if you want to do it free, there's the open security training. And if you want to understand more about Windows internal itself, the trainings by Alex Ionescu and Yarden Shafir, I think those are the best in the space that you could do. Haven't done it myself, but at least from what I heard.
All right. Next question. Which EDR gives you the most headaches to bypass?
There are some. The most headaches, I would say CrowdStrike is still pretty good in what they do. That doesn't mean that it's hard to bypass headaches. I would more say in the sense of the time needed to invest to get around CrowdStrike and or EDRs, and in that case, I think CrowdStrike is pretty top notch.
And that brings us smoothly to the next question. After the CrowdStrike incident, there was some talk about changing the whole drivers in the kernel from third parties. Do you think a big change like this will ever happen?
Very good question. Do I think a change like that will happen? So if you follow the talks by Dave, I think Dave Weston is his name. What they're doing, for example, is they want to write certain components, rewrite certain components of the Windows kernel in Rust. So they have a few initiatives to improve security in the kernel. Will something like this ever happen, that it shifts to a model like in macOS? I don't think so, because at least not in the near future, because Microsoft always has and still has always had and still has an issue with legacy components. So by changing that, they would break a whole lot of currently still working programs. And I don't think they would be able to do that quickly. But I don't have any insights in their plans, of course. So I would
All
say
right.
rather not.
Rather not. Okay, seems like a safe bet. Again, some advice about training. So, what would you suggest for someone who has penetration testing experience but wants to move to a more red teaming, MolDev side? Guides, resources, or advices there?
No. I mean, I'm a bit biased, but of course, if you want to get into the MalDev part of things, there's Suns 670, which I'm an instructor for, where we do teach about how to build a command and control framework. Of course, there are other options like MalDev Academy and Sector 7 that gives you some good introduction into the topic, especially if you want to look at the dev side.
Mhm. All right. And then this one. What are your thoughts on BYVD attacks? Will it be contained through mitigations by Microsoft in upcoming years completely?
Also, a very good question. Will it be contained completely? Maybe. With virtualization-based security and hypervisor-based code integrity already being default on Windows 11, I think that already does a lot in mitigating some of these attacks. Attacks are still possible, but I think Microsoft is doing a lot to mitigate this. And for example, taking away all the memory leak primitives already makes us a bit of a pain in the ass to get around things like kernel ASLR. So it will become more difficult.
All right. New questions keep coming
Mm-hmm.
in the chat, but taking the timing into account, I propose we wrap up here.
Mm-hmm.
Always feel free to reach out to us or to Kevin if you want to discuss these topics more in depth. I want to thank you all again for joining today. I want to thank you, of course, Kevin, for presenting. These webinars, we organize them regularly. They're organized by us, by Enviso. If you want to know more about what you're doing and what we are doing currently on the screen, it's our web address, it's our socials. We post there regularly. We also have a blog where we post more technical, in-depth stuff. That's blog.enviso.eu. All of those resources are available to you. And as I just said, if there is something here that you want to discuss further with us, don't hesitate to reach out to us. We're here to have that conversation. All right. Thank you all. If it's lunchtime wherever you are at the moment, I would say enjoy your lunch.
All right. Thank you all for listening. Take care.